So you'll have some time. Whoa, some time to. I mean, if you want to finish the 8.3 worksheet before you do the 8.4 big ideas, like after the lesson, then that's totally okay. Why don't you just give me your attention for a couple minutes as we go through this stuff? So we're talking about more proportionality theorems. We've looked at a couple theorems recently. Remember, what theorems do we bring back? Yeah, we brought back side angle side. What other theorem?
Whoa. Whoa! Calls down the police. Uh-oh. He was actually coming off.
Geez, well, bringing all those out. There's some entertainment for the virtual students. We talked about side angle side, right? What other theorems do we bring back?
Side.
Yeah, side. Do we bring back any other theorems? No. What new theorem did we learn that we can show that two triangles are similar? Come on, what theorem did we bring back? It was from Thursday. It starts with an angle. A new theorem, a new one. Angle, similarity theorem. Guys.
I don't remember that.
Angle similarity theorem. Two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Right? That was the new one.
Yeah.
Perfect. Hey, Nate, we don't need our phone out right now. Oh, we're not supposed to be doing our worksheet either, so 0 for 2 on that one. Alright. So 8.4. So those are the theorems that we've talked about so far. We're going to look at a couple new theorems today. That's what the learning part gets saying. Triangle proportionality theorem. So this is like the title of our lesson. This is our go-to. This is the big one for today. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportional. So I'll let you, those that are writing things down, I'll give you a second to get that written down because that's kind of wordy. There's kind of a lot there. So I'll give you a second. So like I said, that sounds kind of wordy. Here's, if we're looking at our picture, we have our main triangle, and we have this side over here, QS, and we're saying that it is parallel to TU. Alright, since those two lines are parallel, what this theorem is telling us is that Q, it says right here, perfect, even better. We'll go in this order. RT, so this side length right here, over TQ has the same proportion as this opposite side. As the side across from it. So the two sides that don't have any parallel lines going on would have the same proportion. Pretty crazy. Your mom would probably think that's pretty crazy. So as you can imagine, we'll give problems, we'll give a triangle, ask if the two sides are proportionate, we'll give a triangle that has x involved, and you'll have to solve for x. Kind of the same types of problems that we've been looking at, even a lot of the same strategies to solve, where we we will inject. I see the video on the top right hand side of your screen. Not anymore. But you can see how we'll have the same approach to these problems, setting up a proportion and trying to solve. Now does anyone remember what converse means?
Opposite.
Yeah, kind of opposite would be a good way to look at it. Yeah, reverse would probably be a better word. Let's see, if Allie studies for her test, then she will do very well. If Allie does very well on her test, then she studied. That would be an example of a converse. It's just switching the order around. So what we were saying here is that if we have a triangle in those two parallel lines, I'll read the wording a little better. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So we're starting with the parallel line. We're saying if we have these parallel lines, then the two sides are divided proportionally. Now in the converse, we're saying if some random line, we don't know if it's parallel yet, divides the two sides of a triangle proportionally, then it's parallel to the third side. So hopefully you see the switch there, how the order changes. All right, so let's look at an example. In the diagram, we've got two parallel lines. And it gives us the measures that are right on the diagram. It wants to know the length of RQ. So this is what we would be looking for right here. Now remember, when we set up our proportion, when they set up the proportions here, notice that they put RT over TQ, that we have the longer side over I shouldn't say the longer side, the longer section over the shorter section, and it's all that same side of the triangle. In other words, notice that they don't put RT over RU. Okay, so we've been pretty loose, and I'm not saying that that wouldn't work for sure, but we've been pretty loose with what sides we choose and what order we put them in. It looks like here that we're being a little bit more detailed. So if we look at our example, in the diagram, the parallel, we've got our numbers, we want to find RQ. If we're sticking with what the theorem said, we would put 9 over x is equal to 6 over 4. We would cross multiply to get 36 equals 6x. And x equals 6. Is that anything crazy? It's pretty much exactly what we've been doing, except now we're just working with one triangle, right? If you wanted to, I mean, you can see, if you wanted to put x over 9, set up your proportion like this, equals 4 over 6, it would have worked out just fine as well. But we need to keep, I mean, we have UR, this whole side is in one proportion. And we have the side we're comparing it to also in one proportion. So just be a little more careful. Check your answer too. I mean, we got x equals 20. Would that make sense? Heck no. All right, now we're stepping it up a little bit. 3 parallel lines theorem. You thought 2 parallel lines was a lot. Now we've got 3 of them. If 3 parallel lines intersect 2 transversals, so you can see our vertical lines are the parallel lines, then they divide the transversals proportionally. Kind of interesting. this is not something that we're going to, like when it comes to the test and things, this is not something we're going to totally focus on to be super, what is that?
What does it look like?
This is a wolf and a boy and a baboon. I don't know. Jack, get that thing off the screen.
It's not playing.
I don't care. Turn it off.
Oh, are those?
Three parallel lines, divided transversal and proportionally. Is this not enough entertainment for you, Jack? Come on. Ridiculous. I think this is our last example. Oh, just kidding.
No.
One more example, one more theorem, one more example. You guys are doing good. So here's a real life example for you, in case you're missing one. Hopefully this is better than our, well, I hope you already did this. So it is better than the one on Friday with the ramp. Those that were here got to see a super good real life example of a ramp or a fort. Which one was it? Was it a ramp or a fort?
It was like a fort, but that had a 9-foot side and a 6-foot side.
Yeah, the ground was a little uneven. Yeah.
Your wheels had to be level.
Yeah,
Like this.
we were trying to level it off.
Yeah.
That's why they needed to be similar size, right?
Yeah.
To keep it level. Thank
Thank
you, Will. Here's another real life example for us. In the diagram, angle 1, 2, and 3 are all congruent. Sweet. GF, they tell you all that in the diagram. Find the distance of HF between Main Street and South Main Street. Let's see. H is here. F is right here. Now, you're probably thinking, why did they tell us that 1, 2, and 3 are congruent? Well, that tells us that we have parallel lines right here. Okay? So that's the importance of knowing that those angles are congruent, that we have 3 parallel lines, so we know that our rules apply. Now, if we are trying to find the total measure of HF, does anyone have any idea of how we would go about that? Any idea at all? We already know GF, so we're kind of in good shape there. We kind of have a head start. Really, if we could find HG, that would be off the top of my head. I'm not sure. We can look. We need to set up a proportion though, so that we could find HF. Why don't we just start by trying to find HG, and then we'll go from there. Because if we find HG, we can add 120 to it, and then we're all good. Remember with our theorem, we said that if we have 3 parallel lines, where'd it go? There it is. That UW is proportionate to WY. So we can set something up here, since we have 3 parallel lines, to try to solve. So if we have x over, now what would be the denominator here for our proportion? Looking at our theorem, what would be? 300? I think we could set it up like that and it would work. If we totally follow our theorem though, we see that UW is over WY and that those are on the same line. We see how those are all on the line L. So when we set up our proportion, we probably would want to put x over 120. See how we used distances that were on the same line that cut our parallel lines? Just like we said to in the theorem. Yeah, correct. Now I think there are other ways we could set it up and we'd be okay. What's 120 times 300? 3,600?
Yeah, 36,000.
36,000, that's 0 off. Now when we divide that by 150, what does that give us? 240? So x equals 240. Are we done? Yeah, we got to add the 120. So 120 plus 240 would give us 360 yards.
Oh wait, I was right.
Good job. Now hopefully, I mean, I set up the proportion the way that the theorem stated it. It's just like, yeah, that works. But just like Hannah said, we could set up the proportion in a little bit of a different way, still get the same answer, but this is the way the theorem is stated, so I think this is the easiest way to set up our proportion. Or just like grading, close your eyes, multiply by 3, and hope for the best. That seems to work. All right, last theorem, and one more example. You guys are doing good. Kylie, you doing okay? Okay. 8.9, triangle, angle, bisector theorem. We need to come up with better names. If a ray bisects an angle of a triangle. Remember what rays are? Do we remember that from way back in chapter 1?
It's like a line that goes in one direction.
Yeah. Yeah, perfect. If a ray bisects an angle of a triangle, then it divides the opposite sides into segments whose lengths are proportional to the lengths of the other two sides. Okay? The key is that this ray, like it says in the very beginning, this ray bisects angle C. So that means, like the tick marks say, both sides, angle C is split in half. It bisects it. Then, AD over DB is proportional to, where's CA? CA over CB. Again, when we set up these proportions, we probably could set it up in another way and still get the same answer, but they keep, and we're going to do the same thing, they keep the side that is split in one proportion, and they keep these other sides, the remaining sides, in another proportion. So we'll just be a little bit careful when we set this up. Take a look, and I know a lot of you guys have the slides up and write things down, but in the diagram, Q, P, R is congruent to RPS. So, in other words, this red line bisects angle P. Use the side lengths given to find RS. So we're looking for X. Who can tell me how we set up a proportion? This one's a little bit tricky. We need to set up well, we have two ratios, right? We need one ratio that has to do with this side, and one ratio that has to do with these leftover sides. 15 over x. Well, like I said, this one's a little bit tricky. We're going to have to adjust a couple things. Do we know, let's start here. Do we know that 7 over 13 is going to be one of our proportions? Hopefully, those are our remaining sides, right? QS is split. So 7 over 13 are the two leftover sides that we're not talking about. Now, if we look at QR, do we know what that side is? No. What do we know about QR? It's what? Yeah, it's exactly what I'm looking for. We know that QR is 15 minus x. Hey, stop.
What do you mean cheat?
We know that QR is 15 minus x, right? Whatever x is, we subtract 15, that'll give us QR. We know that RS is just x. I'm not making it more complicated. No, this is what you are doing, except you cheat. Can we cross multiply and solve this? Couldn't we? We can? Hopefully. 13, 15 minus x equals 7x. 15 times 13. Somebody, you guys all have calculators out. Come on, let's go. 15 times 13. 495. $195? So quick. This doesn't seem like it's going to come out clean, does it? What the heck?
I'm telling you, but.
You're telling me I did it the complicated way?
Mm-hmm. Yes, you did.
No, I didn't.
No, not yet.
No, you guys just must be wrong. What's 195 divided by 20? That's the correct answer. So whoever said 5 was not correct.
I just said 15.
See, close your eyes and divide by 3.
Sometimes it works. That's not
Yes, it is. Well, maybe not drawn to proportion, but
because if that one side's 15, that's the same numbers.
no, that seems about right. If PS
Oh, wait,
is
never mind.
yeah, that seems about right. Any questions? We went fairly quickly through the theorems because I think the examples are a little more helpful. We're just setting up proportions like we have been. Rylan, questions? Allie? Good? Nick? Okay, cool. Well, stop